Now let's look at zero and unit indexing in while loops. First, let's talk a little bit about counting. Suppose you were running a race and you were supposed to go 3 laps around the track. What happens if you say 1 as you're leaving the blocks? Well, this is basically unit indexing. So you leave the blocks and you say 1. You go around the track once. Whoop. That's 2. Then you go around the track a second time, and that's 3. So you've counted to 3, but you've only done 2 loops around the track. That is a problem. Won't win many races that way. So let's talk about a pattern that's called unit indexing. Suppose you want to write a loop that prints out 1, 2, 3. Well, let's trace the code below. We have int count is 1, and then we say while count is less than or equal to 3. In the loop, we'll print out count, and then we'll increment count by 1. Well, here's what happens when you trace this loop. Count is 1 initially. Count less than or equal to 3 is true, so you go into the loop. So you print out 1, and then you increment count to 2. So that puts us at this point in the table. Then count is still less than or equal to 3. So you go into the loop again, you print out 2, and you increment count to 3. So right here we are in the table when count is 3. Now count less than or equal to 3 is still true, so you go into the loop again, you print out 3, and then you say count is count plus 1. So count actually ends with a value of 4 at the end of this loop, even though it printed out 1, 2, 3 successfully. That's an interesting problem. Now let's look at a second pattern. This pattern is called zero indexing. We're doing the same thing. We're trying to print out 1, 2, 3, and we're going to trace the code again. So we start with count is 0, and then we look at while count is less than 3. Now this time we have to increment count first, because the first thing we wanted to print out was 1, and right now count has the value of 0. So we increment count to 1 and then print it out, and that's what we repeat. If we trace the loop now, we'll see count starts at 0, gets incremented to 1 in the first trip through the loop, then we print out 1, then we check to see if count is less than 3, which it is, because 1 is less than 3. Then count gets incremented to 2, we print out 2. We say while 2 is less than 3, well that's true. So then count gets incremented to 3, and we print out count being 3. So there we have it. We're still printing out 1, 2, 3, but we're doing it differently. Now what I want you to pay attention to is the pattern between these codes. So we started with count is 0, and we ended with count less than 3 when we were zero indexing. Whereas with unit indexing, we started with count is 1, and we ended with count less than or equal to 3. That's a pattern that's worth remembering. One thing you may be wondering is, why did I stop at 3? Well, there's a very good reason for this. When you start tracing a loop more than 3 or 4 times, it's really easy to lose track of where you are, and then you just can't be accurate enough. So the reason I like 3 is you have an initial iteration, sort of a middle one, and then a last one. And that seems to show up most problems that are in loops. And so that's why you'll see me use 3s a lot when I'm working on examples. The technique that I use to figure out what the loops we're doing is called tracing code. And this is another way that we visualize how programs work. Each column records the values in one variable as they change over time. So one of the things that's nice about tracing code versus memory diagrams is with tracing code you actually see the changes over time a little bit more clearly. Sometimes in memory diagrams, when you start crossing things out, it gets a little bit messy. The value at the bottom is the current value. So that's the one, for example, when the loop ends. Now, it's hard to be accurate for more than a few iterations, so I don't recommend that you try to hand trace things that go through 10 or 20 iterations. I certainly couldn't be accurate enough. Instead, cut it back to a smaller number of iterations and pay attention to the pattern. If the pattern is the same, you'll still be able to pick up the errors. So here are some general observations. Unit indexing starts at 1. Remember, when we use the word unit in the mathematics sense, it means 1. It ends with less than or equal to the goal, which in this case was 3. But when you end, the counter is going to be 1 larger than the goal. And that can be a problem sometimes. Sometimes we want to use those counters later, and having them a little bit too large doesn't help. Now with 0 indexing, we start at 0, and we end with less than the goal, which again was 3. But the counter equals the goal at the end. And so that's kind of a nice thing. This is one of the reasons that computer scientists tend to prefer 0 indexing over unit indexing. But I do want to point out that most loops can be done successfully either way. Also pay attention to the fact that we had to change the order of incrementing the counter. So you still have to pay attention to all those minute details that you're always watching for in loops. Now this is part of something in computer science that's a big part of the culture. It's called an OBOB. And yes, that really is what everybody calls it. This stands for off by 1 bug. Now this can be a very hard mistake to find. And it is incredibly common. In fact, it's one of the most common mistakes people make when they're writing loops. What it means is you go through the loop 1 too many times or 1 too few times. Something other than the right number. So either way, going through 1 too many or 1 too few really is a big problem. Now, computer scientists are absolutely insane about how important this is. And the reason that we're so insane about it is because it causes so much trouble in software. So this is something you definitely want to pay attention to every time you write a loop. In fact, I recommend that you do a little bit of tracing before you even run the program to see if it's working correctly. I know that sounds like it's a lot of work. Sometimes it's easier to trace things first than it is to debug them after they're done. So keep programming.